find the button. All right, so tonight we're kind of combining two sections. In the first half, we're going to talk about A/B testing, and in the second half, we're going to talk about Bayes' theorem and Bayesian statistics. So to start off, A/B testing. If you haven't heard of it before, it's a sort of experiment that's often done with website designs or mobile apps, where basically a company serves two different versions of something to different segments of its customers. And then it can measure some metric, whether it's like conversion rate, whether they buy something, whether they click on an ad. And then they can compare the two groups and use statistics to say whether or not one option is better than the other. So to dig into that, we'll first import some libraries we're going to need. Give it a second or two to run. All right, so consider this scenario. Your company wants to test a new website layout to see if it can increase the chance of a purchase for each visitor. So the current layout is estimated to generate a sale 30% of the time. And you need to test whether or not the new design will increase that proportion of sales. So you need to run a test that will allow you to statistically detect an increase by at least 10%, and with a confidence level of 95%. So how would you go about doing this? Previously, we've been doing hypothesis tests around sample means, but this is asking about a proportion, a percentage. So it might be a little different. So the hypothesis for this is kind of similar. So the null is just that the purchase chance for both are equal. And then the alternative hypothesis would be that the purchase chance for the new layout is greater than the old layout. So the first step for A/B testing is to determine your sample size, because you don't want to run the test and then realize that you didn't collect enough samples to be able to accurately say what you're trying to prove. So to calculate sample size, we can use the solve power function from, I believe, stats models. So we can first calculate the effect size using this proportion effect size function from stats models as well. And then we can pass in the alpha that we want, which is 5%. And then we can pass in a power that we want as well. The standard is usually 80% power. And then we can also pass in the alternative hypothesis, whether we want basically a 1 or 2-tailed test, whether we want to see if it's greater or less than, or whether it's just different in general. And then this will give us some number back. It'll be like a decimal place. So we're just going to round it up because we would need a whole number of samples. So using this, we can plug in here. So it's going to take the current proportion of the population. So right now we're getting a 30% conversion rate to a purchase. And then we want to detect a difference of 10%. So we pass that in here. And then we want to see if the new layout produces a larger proportion. So the alternative here is going to be larger. And if we run this, we see that we would need a sample size of 280. So what that means is that in both groups, we would need 280 customer samples. So we would need 280 with the old design and 280 with the new design. So to test this then, we need to use what's known as a 2-sample proportion test. It's going to be similar to a 2-sample test for means, a difference of means, but it's a little different since now we're dealing with a proportion. So we can just store our sample size here as n, and then we're going to generate some random data. So in this case, a 0 will mean that someone visited and did not make a purchase, and a 1 will mean that they visited and made a purchase. So you can see here that A, which will be the old layout, it will basically just have a 50% chance, but then group B will make it so that it's likely to have a greater than 50% chance of making a purchase. So we'll go ahead and run that, and then we'll make a data frame of this data to kind of visualize it. So we're just going to make two columns, yes and no. So yes, they purchased something, no, they didn't. And then our two groups, A and B, where A is the old layout and B is the new layout. And we can kind of set this up so we get this nice little table here. So to read this, so we have our old layout here on the first row. You can see that 134 converted basically, and 146 did not. And then for group B, we can see that more converted than did not. And if you add the rows together, you should get the 280 for both of them. Let's see. So this, I think, was a formula. Give me 1 second here. I'm just gonna pause recording. All right, so for a two sample proportion test, this formula here will give us our Z value. And then the P stars within there, that's basically the overall total probability. So N1 times P1 will give us basically the number of times that we got a 1 for the first option, and then this will give us the number of times we got a 1 for the second option. And then N1 plus N2 is overall how many samples. So this will tell us for both combined the odds of getting a 1, basically. So using this formula, we can make a little function here to calculate a z-test for two proportions. So we find P1 and P2. Okay, so X1 and X2 as arguments here, those are basically how many yeses we got in the group. So for our data frame, I think we had, let's see. Okay, so for group A, so our X would be 134, and then for group B, it would be 166. So that's what we're gonna pass into the function, and then we also pass in how many samples were in each group, which in this case, they're equal, so it doesn't make a huge difference. So then P1 is going to be the number of ones in group A divided by the number of samples in group A, similar for P2, but with group B. And then we can use this formula here to calculate P star. And then the standard error is going to be the denominator. So we'll calculate that separately. And then finally, the Z value is just the numerator here divided by that standard error on the bottom. And then we can use that Z value to find the corresponding P value using the CDF of a normal distribution. And then we can return both the Z value and the P value as well. So if we run this with our data here, so we're going to pass in the number of yeses for group A, and then the value of N, number of yeses for group B, and then N, since both of them had 280 samples. So if we run that, we get our Z statistic, and we can see that we get a significant P value of less than the 0.05. So in this case, we would reject the null and say that there is a difference in the proportions between the two groups, and that group B has a higher percentage chance of conversion. So another way to do this is using what's called a chi-squared distribution. This is another probability distribution that we haven't covered yet. So I'll kind of go over where it comes from. It's basically found by taking a standard normal distribution and squaring all the values. So here's a standard normal distribution, and then here would be a chi-squared distribution with 1 degree of freedom. So you can think of it, all the values in the normal distribution less than 0, when they get squared, they're all going to become positive. So you can see that it kind of moves everything over. It becomes a lot taller as a result. So So chi-squared is dependent on a value of k, which is the degrees of freedom, and this changes the shape of it. So what you just saw was chi-squared with a k of 1, but this shows you for value k equals 3 through 7. So you can see as k increases, it kind of shifts the distribution to the right, and it becomes shorter. So chi-square distributions have some interesting properties. For one, the mean is always equal to k. So if we go back, the average value if k equals 3, so this blue line is going to be 3. So at that point, half the area would be on the left and half would be on the right. Another property is that the variance is equal to 2k. So if our k is 4, then our variance we know would be 8. And lastly, the mode, so the most common value, is just going to be k minus 2. And obviously this only works for k greater than 2. But to kind of visualize that, we can take, for example, k equals 7. And if we subtract 2, we get 5. And we can see that 5 would be the highest point on that distribution. And if we go to k equals 5 and subtract 2 and get 3, we can see that that also is the highest point or the mode for that distribution. So that's chi-squared. The degrees of freedom for chi-squared are calculated with this formula, c minus 1 times r minus 1. This means c is the number of columns and r is the number of rows. So in our example, remember in our data frame, we had basically 2 rows and 2 columns. Our rows were group A, group B, and then our columns were yes and no. So that would be 2 minus 1, which is 1, and 2 minus 1, which is also 1. So that would be degrees of freedom 1 for that specific example. But you can see if we had multiple groups, if we had 3 groups instead, then our degrees of freedom would be different, and we would have a different chi-square distribution. So to calculate chi-squared, you basically sum up the difference of the observed values and the expected values, and you square that, and then you divide by the expected value. So this is kind of similar to when we were doing expected value before with probabilities. So if you look here at our data frame, let's see. So the expected values are going to be found by basically summing up all the yeses and finding out what proportion overall that is. So we would take 134 plus 166 and get 300. And then that would be divided by our total number of samples, which would be like 560. And we would do the same thing for the no columns. So we're going to make a function to do this. It looks a little complicated because it's kind of a lot of calculations, but there's going to be an easier way to do this here in a minute. So first of all, we have to find, let's see. So we're going to pass in same thing as before. So the number of yeses for group A, the number of samples in group A, the number of yeses in group B, and the number of samples in group B. And then we can find the number of no's for each group by just taking the total number of samples in each group minus the number of yeses. And then we can find the expected probability of both yeses and no's. And then we have basically 4 different scenarios. We can have group A yes and no, and group B yes and no. So for each of those, we use this formula that we were just looking at and take the observed value that we got, so what's over in our table here, subtract the expected value, square that by the expected value. And if we do all that and add that up, we get our chi statistic. And in the same way we do with normal distribution, we can just do a CDF on it, pass in the chi value, except we also have to pass in a k value here. So this, I think it's k. This is the degrees of freedom. So as I showed before, since we have 2 rows, columns, if you plug that into the formula, you get 1 degree of freedom for that. So if we go ahead and run this, pass in our data, and print out the z statistic and the p-value, we can see that we get the exact same result. So it turns out that with two sample groups, a z proportions test and a chi-squared test will give the exact same results. So now the quicker way to do both of these are basically built into stats models. You can just do proportions z-test and proportions chi-squared. You just have to pass in the number of yeses basically for both groups, and then the number of observations in each group. And it'll do all the calculations for you, give you your z statistic and your chi statistic, and then give you the p-values for both, and they should always be equal. So now what if we want to test more than two groups? Well, in this case, our null hypothesis, this is kind of like ANOVA, except we're doing proportions, so it's going to be a little bit different. But basically, it would be that all the proportions are the same. And then the alternative would be that at least one is different. We don't know if they're all different. We don't know one, but we can at least say that at least one of them is different. So in this case, we're just going to have to simulate some more data. So we're going to add a third website option, a layout C. And again, we're just going to simulate that by choosing a bunch of random zeros and ones, but kind of weighting it for the different groups. So like group B is more likely to get a 1, whereas group C is more likely to get a 0, and group A is just a 50-50 chance. So if we run this here, we can get this data frame below. We can see that group C definitely had a lot less yeses and more nos. Group B had the total most number of yeses, and then A is somewhere in the middle. So this is where chi-squared is important, because you couldn't really do a two-sample z-test with 3 groups. But with chi-squared, you can do any number of groups because it changes depending on the degrees of freedom, which is dependent on columns versus rows. And in this case, we have 3 rows or 3 different groups. So it'll actually be a different chi-squared distribution. So all we have to do is run the same code, basically, pass in our yes column. There's just 3 rows in it now, and then pass in the number of observations in each. And that will give us a significant p-value again, which isn't too surprising since that group C is really low compared to the other ones. So the p-value says there is a difference in proportions between the options, but where's the difference? Just like ANOVA, we don't know exactly where it is. So unlike ANOVA, there's no Tukey's HSD for proportions, but we can kind of recreate something similar by using what's known as the Bonferroni correction. This basically adjusts for when you're running multiple pairwise comparisons, and the p-values can kind of add up, as we showed in the one lesson. So it basically corrects for that, and it will lower your overall p-value threshold so that you have to get a really small p-value for it to still be significant. So to do this, all you do to find your adjusted alpha is take your regular alpha divided by the number of comparisons. So in this case, we have 3 different groups. We have 2 different outcomes. So there's going to be 3 different comparisons, basically. So A and B, A and C, and B and C. So that's 3. So if we take our alpha, 0.05 divided by 3, we can get our adjusted alpha of 0.016. So now if we run chi-squared for each pair, so in the first one we're doing just A and B, so we're dropping C from our data. If we run that, and then we can do the same for A versus C, we just drop B out of the data frame, and then the same for B versus C. So what you get back here, the first value is the chi-squared statistic, and then the second is the p-value. So if we look at these p-values, we can see that only the last one is less than that 0.016 of the adjusted alpha. And then the other thing that this returns, these arrays here. So if you look on this last one, the 149 and 131, that's basically diagonally here. So the number of yeses for group A, or wait, let's see. No, the 149 is this row because we're comparing B and C. So it's basically this row here, and then the 108 and 172 is what we're comparing it to. And then I believe the second part is the expected values. So from this, we saw that we only got significant results for B versus C. So from this, we can say that C is definitely worse than B, but we can't actually say whether C is different from A or if A and B are different. So what would be suggested from that then, if you're working for this company, is to, if you like had to drop one of them, you could drop C, but really you should probably investigate the relationship between A and C some more, because there's still a chance that A and C are the same. All right, so now combining all this, we're gonna do an activity like usual. So everybody has been to a mall, I'm guessing, and has seen those people at the kiosk in the center who try to coax you over and get you to try like their fancy face cream or whatever it is. So a company has been trying to basically increase their performance in that and increase the chance of someone coming over and being enticed and buying their product. So they think it's due to company dress code. Most of them dress up in nice suits or dresses. They think maybe that's too formal for people and turns them off. So they're going to try having their employees dress in animal suits and see if they get a higher conversion rate doing that. So your task, they've already actually ran the test, which is what they shouldn't have done because they didn't consult their data scientists first. So you have to first make sure that they even gathered enough data to be able to detect an increase of at least 3%. So you'll have to do some sample size calculation there. Then you'll have to decide on your hypotheses, choose the appropriate test, calculate the test statistic, and summarize the results. And this is just using the, let's see, I didn't include it here. What's the file called? It's like, it's trialresults.csv. So go ahead and pause recording.
Okay, so the first thing we had to do was build our hypothesis, which was that our null hypothesis was that the old dress code was going to be the same as the new dress code, or our alternative hypothesis is that the new dress code will increase the conversion rate. Okay, so the first thing we had to do was make sure that we have enough in our sample size to see if we could run this. So using what was given to us before, P0 is our current proportion, which we want as 8%. The P difference is at least 3%, and our alpha and power we assume is the same as 0.05 and 0.8. And because our alternative hypothesis is that we want it to be more, it's larger. And so we get a sample size of at least 1,175. And after we found out what it was, we actually had a sample size of one more, of 1,176. Here is our table that gives us the number of bots and decline. So from there, we could just use we could either use the chi-squared or the proportion z-test, but because this was only 2 groups, we used the z-test with our sample, and we got a p-value that was less than our alpha, which means that the purchase rate increased by at least, that means we could reject the null hypothesis, which means that it increased by at least 3% with the new dress code.
So just a note on that 3%, you'd have to actually look at the effect size to see if it is 3%. We just wanted to see if we had enough data to detect at least 3% of a change, if that makes sense.
So what would I then, but this part, right, reject the null hypothesis is okay?
Yeah, that's good. So then you can accept your alternative hypothesis, which was?
That the dress code, the new dress code increased the conversion rate, right?
Yep. Mm-hmm.
Okay, thank you. Wait, can I stop sharing?
Yep, good job. All right. Do we have any more questions on A/B testing before we move on to Bayesian statistics? Nope. All right. I'll pass it off to Raphael then.
All right. Cool. So we're going to talk about some Bayesian statistics, really like asking the question, why does prior probability matter? This is a very, I don't want to say it's a heated topic in statistics. I would hope no one is a frequentist at heart. A/B testing falls under what we call a frequentist model of stats. Bayesian statistics falls under this other paradigm. And a lot of people think of them at odds. I think of them more like, what's your problem? You need to employ one or the other. So the objectives for today, you are gonna have to use pandas to manipulate data to solve these problems. So heads up on that. Also, just to apply Bayes' formula to solve these questions and the activities, and these are like very apropos things to what you'll be seeing later. We're just gonna go over Bayes' theorem. I'm gonna talk about multi-arm bandit for a little bit, which is like where the frequentists and the Bayesian models kind of like meet and have their odds a little bit. Then you have to like kind of pick one over the other. Then we're just gonna go through an example doing Bayes, and then that's it. Okay. So the first thing is this is Bayes' formula. It's the probability of x given y. This is the notation. Just for anyone who doesn't know the notation, this bar means given. So in general, the probability of A occurring given that B has occurred equals the probability that of B occurring given that A has occurred times the probability of A divided by the probability of B. And so like, for instance, the probability that you will eat breakfast given that you woke up at a certain time, right? Like that has a certain probability to it, right? If you woke up earlier than usual, it's probably got a higher probability. If you woke up 10 minutes late for work, you're probably not eating, you're headed out the door, right? So all those things are Bayesian statistics. So I want to talk about multi-arm bandit, and then we'll get into an example. So multi-arm bandit comes from the idea of, and it shows an octopus here, it's like the classic picture, pulling on slot machines. So imagine that you are gambling at a casino and just doing slots. And at first, there is like an equal chance, and let's say there's like 10 slots. You choosing a slot is like fairly random at the beginning, right? Maybe you pick 1, 2, maybe you pick 8. I don't know. But then as you start picking them, you find that slot 4 starts paying out more often than other slots. What multi-arm bandit would start doing if you employed this model, which you probably will intuitively, is you will just pick machine 4 more often because it's paying out more often. And so every time you pull on it, you have a higher probability of getting a payout. Now, what are the pros and cons to doing that? I'm asking. This is like a little mini discussion.
Well, it's kind of, there's a fallacy in there. Like
okay, what's the fallacy?
The gambler's one. Just
Which
because one machine is doing one thing doesn't mean that another machine is going to do something else.
That's true, but we're not saying these are dependent, right? They're all independent machines. What we're more saying is like, as you've just gone through and put your coins in and pulled them, machine 4 has just paid out the most often. So we're not like making it dependent. We're not saying if machine 4 pulls and it pays out, then it affects machine 8 or something. So what are the pros and cons to that?
Pros, I guess, are that you naturally optimize your returns, right? So if machine 4 pays out at a higher frequency, I think the way multi-arm bandit, if I understand it correctly, works is it'll just pull 4 more and more and more and more often until it's almost just pulling 4 all of the time.
Okay.
And then if 4 is actually the most, pays out the most, you'll actually, it optimizes, I guess, like your efficiency and your effectiveness.
Sure. Yes, and that's a big if, right? If machine 4 is the best machine, then you will optimize things. But so what is the con then?
The con is because you start pulling 4 more often, it's a self-fulfilling prophecy almost.
Yeah, you can kind of think of it like that. It's also like, let's say machine 8 just takes a few more pulls to start paying out more often, right? Let's say, so like you're not exploring other options anymore, and I mean, it's just like the quintessential millennial kind of thing, right? Like FOMO, right? Would just totally explain what you're doing. You're missing out on exploring other options that could be paying out at a high rate also, because you're just trying to maximize 4, which might not actually be the best option. So in multi-arm bandit, there's this balance between exploitation and exploration. So even though 4 wins most of the time, you can set it up to where every like so many pulls, you just randomly pick a new one to see what happens, right? And so the way this would work is you would have machine 1, machine 2, machine 3, machine 4, and let's just do 5 just for the sake of simplicity. And we're going to just draw some PDFs, and we're going to just put them all to be uniform. So here's what they start looking like. So they're all uniform probabilities, which means you pick one at random. Now let's say this one loses. And this is like 50%. And this is the chance of you picking this one again. Like down here is the probability of you picking this one again. Well, when it loses, you would update its distribution, and it would then look like this. And so now the chances of you picking it have gone down, right? Like it's mostly like a 30% probability of you picking it or whatever that number is. And then let's say you pick this one and it loses. You pick this one and it loses. You pick this one and it wins. You pick this one and it wins. Then the chances of you picking one of these two is the same. And so you might pick this one and it loses. And so you update its distribution. And as you're picking them and as they win, these distributions just keep getting updated. And depending on like who's got peaks over here, like on this side of that line, that's who you're gonna pick. So machine 4 would have more wins, which means like you're probably gonna pick machine 4 most of the time. But you could have one that's fairly close, like machine 3 might be, kind of in the middle. And so you can actually adjust a parameter to like be greedy or not. And there's actually a thing called greedy epsilon, which is like a method of multi-arm bandit that just hammers it home. It's like exploit, exploit, exploit. If it starts winning, we're just picking it until it's no longer the best. Which probably isn't the best thing for most scenarios, but it is just a way of doing multi-arm bandit. And so essentially this is what it would look like. Like one machine would be doing better and you just have a higher chance of picking it until it no longer does better. And that is like a huge benefit. Oh, I don't have this image up. Let me see if I can pull it. Is it this one? I think it's because the image was super tiny. Yeah, but this is the difference between A/B testing and bandit selection. Is like A/B testing, you run a test for like a given period of time. And then you say, all right, after 5 weeks, A is the best. Therefore, we'll use option A. Right? Bandit testing, after a week or so, however long you want to take to evaluate it, you would ask, well, which one's doing the best? And if you saw that it was A, well, then you would start giving A to more people or serving A more often or doing A more frequently. then you would look at the next week. Well, did A still outperform everything? Yeah, A still did really well. C did pretty not well, so like it went down quite a bit. B went down not so much. Then the next week, C is virtually, we're not serving it at all anymore because it's just not good. B is getting smaller and A is definitely like taking up more space. And then by week 5, where we're still testing all 3 options, here we are pretty much using the best solution by that 5th week. And really, like after week 2, over 50% of what we're serving is A. So a benefit in that is like, if you're doing something like serving a web page, you would want to use bandit modeling. If web page A increases engagement, keep serving web page A more often, right? Quit serving, and if C is not, right? If it's clear after a couple weeks C is not serving well, get C out of there. Like, why would you waste so much time just to like waste time? It's really just wasting time. Like, you want to optimize your engagement as fast as possible. Versus A/B testing, which is like, it's against the paradigm to do that in A/B testing. In A/B testing, you have to test it for like so many iterations or like for so long of a period of time. Like, there is no other way to do it. So A/B testing is definitely used for like medicine, right? We would not want to do bandit testing in medicine. That would be horribly irresponsible, right? Just, oh, this looks a little better. Let's just give you this one now. Like, that's not a good idea. But if we're serving something like a web page or an ad or a banner ad or something, like something that's not going to get anyone hurt, you can definitely use bandit modeling here. And bandit modeling is awesome. It's super fun. You don't want to do it with medicine or like testing car parts or doing anything where like someone's life is in jeopardy. Like, do a frequentist approach, treat them all equally, give them all an equal shot across the entire board. So that is where Bayesian statistics is like really diverging from what you've been learning. Okay, are there any questions just about multi-arm bandit or Bayes so far?
Comment, I guess.
Yeah.
So A/B testing would be better used in a high-risk environment, and the bandit modeling would be better for a low-risk environment.
Yeah.
When it comes to like human life and stuff, or part
Yeah.
life or something like that.
Yeah. I would say anytime like I mean, I don't know how to explain it other than like there are just some instances you should not do Bayesian or a bandit model, right? Like testing medicine, testing treatments, testing, I don't know what else, but like there are high risk environments where, like investing money, that's a high risk environment, depending on the amount of money. But you would still want to do multi-arm bandit, but you just might want to tailor how often you're exploring, right? Maybe you want to explore more often and check out other options and see how they fare. So, and that's the thing about Bayes is it's like really easy to tailor stuff in it. It's essentially what machine learning is Bayesian statistics. Well, machine learning is based on Bayesian stats.
So part of, I feel like the reason people like, or at least one argument I could see people having in favor of A/B testing is that in A/B testing, the longer you go on and run the test, the less likely kind of external events and factors influence the results. Like let's say option A, everyone picks it week 1 because
hype or something, right?
Right, hype or something. So does multi-arm bandit, if all of a sudden in week 2 option B starts performing better than option A, can it adjust well?
Yeah, because like if you're still pulling A and it's losing, it's going to move that distribution over to a certain amount, right? It's going to pull that distribution, and maybe you're exploring a little bit, so you pull B and B starts pulling ahead, and now you start choosing B more often.
Okay.
I mean, people like using this kind of modeling because it is easy to move around whatever you want to do. Like it's not super difficult, and it's certainly it's definitely better to do this than like an A/B test, unless you want to test something like for web pages for some instance. I guess maybe if you're really just wanting to really know which web page is better, you would want to do an A/B test. But I feel like, because the other thing about this is you can always just like end it and do another one and throw out another web page, right? And just add another one to the mix and see how that performs. So
Right.
it's great. Like I'm a Bayesian monkey. Like I just love all things Bayesian. So
It also sounds like Bayesian statistics is more likely to tell a story.
I don't know. Well, yeah, I would say A/B testing could tell a story.
Well,
Just
it gives you an answer, right?
a short one. Yeah, like we did this and we got this, and that's
Right.
like a haiku of sorts, right?
Mm-hmm.
So, but all right. So this is multi-arm bandit
Okay.
modeling. We don't actually go through it in this course, but it's something that I've actually used, and it was awesome, and I like to share it with y'all because it's just really cool.
I like it a lot.
Yeah, it's fun. All right, so here's just bringing all that down a little bit to like some basic Bayesian conditional probability problems. If a fair dice is rolled, what is the probability that it is a 2 given that it is even? Well, any ideas here?
Is it a third? Are we considering like a 6-sided die?
Yeah, 6-sided die.
Yeah, so 1 out of 3.
Yeah, it's even, so it's a 2, 4, 6. Probability that it's a 2 is 1 out of 3. So that's a fairly intuitive thing to know. You don't really need to use the formula, but here's how you would use the formula. So the probability that it's 2 given that it's even equals the probability that it's even given that it's 2 times the probability that you roll a 2 over the probability that it's even. So this is just plug and chug from here. Nothing super special going on. What happened? There we go. Okay. So the probability that it's even given that it's 2 is 100%, right? If you roll a 2, it is an even. The probability that you roll a 2 is 1 out of 6, and the probability that you roll an even is 1/2, giving you 33% when all is said and done. So some Bayesian problems are going to be very intuitive where you do not need to use Bayes' formula. Some are not going to be like that. Solve it however makes sense to you. I like to use Bayes' formula anytime I'm not certain. Like if it's not 100% I can do this without it, I just use the formula because it's a very nice, clean thing to do. Which brings us to the activity. So here's your first scenario. A family has 3 children. Assuming that boys and girls are equally likely, determine the probability that the family has 2 boys and 1 girl, given the first child is a girl, 2 girls, given that at least 1 child is a girl, and 3 girls, given that the younger child is a girl. Scenario 2, you're given an array of points and their labels. A point is chosen at random. What is the probability that the point is less than 5, given that its label is 0? So here's the data. So you have these points here and their labels here. And this is like a really good problem. This is a fun problem. Like have fun with it. And this is where you gotta do some Panda stuff to like get the information you need. But I would set up the formula. I would make a variable for everything. Like I would have a variable, I'm gonna just go back, sorry. I would have a variable for the probability of B, the probability of A, the probability of B given A. That way you can kind of put all of them together at the end, right? The probability of A and B, and then you kind of like put them together. So definitely want to like set those up well in Python. I also wouldn't be afraid to like type it out, like probability less than 5 given 0. Like It's okay that it's a long thing. It's okay that you're going to have to type a little bit more on your keys. You get a lot less confused when you do it. So, and then the third scenario, very similar. Using the iris data set from scikit-learn, what is the probability that a flower has a sepal length greater than 6.3, given that the flower is an iris versicolor, which is a label of 1. So whenever you look at the iris data set, you will see that there. That's it. Those are the activities. I'm going to stop sharing.
All right, for A, we were looking at 2 boys and 1 girl, given the first child is a girl. So for the probability of A, we did the, what was it? 2 boys and 1 girl. For probability of B, we did first child being a girl. And for B given A was just 1/3. And we got 0.25. Any questions?
Do you know how to solve that without using Bayes too?
No, I would just write it out. Kind of like we were doing in the breakout. Alrighty.
All right, so problem B. Brendan, Bonnie, or Elizabeth? Okay, Bonnie.
Do you want me to share my screen or no?
Yep, if you can.
Okay. So similar to the first one, the A, even A will be if we have 2 girls, and B is 1 is a girl. So probability of A is actually the same with last one. If we have 2 boys and 1 girl, we can use Bernoulli's formula. So if you write it again, that would be like, or you can write all your options, but I'll just do this. Like this is 3/8, and probably of just 1 girl will be all the possibilities and minus if all boys. So that is 1/8. So 1 minus 1/8 is at least 1 is a girl. And so probability of B given A, meaning if at least, given 2 girls, at least 1 is a girl. So that probability will be 1. So using Bayes' formula, we get the 3/7.
All right, that looks good. All right, and part C.
I can do that one.
All right. I think you're muted, Beth.
Good call. For part C, their probability of A is that all 3 children are girls, and there's a 1/8 chance that that will happen. The probability of B is that the youngest is a girl, and there's a 1 out of 2 chance that could happen. And then the probability of B given A talks about how there are 3 kids, and out of those 3 kids, how many of them are girls, and what is the probability of the youngest one being a girl. Since all 3 of them are girls, there's a 100% chance that the youngest is a girl. And then this is Bayes right here, and you end up solving and getting a 0.25 chance that there are 3 girls given that the younger one is a girl.
All right, cool. Thank you. All right, Raphael, do you have any closing remarks on Bayes?
Yeah, sorry, that was more difficult than I anticipated, so I apologize.
I think the biggest takeaway is that, yes, it's a little more complicated
Yes, and
than
then
I originally
also
think.
I would like to share with you how I label my just so you can see it. Like, this is how I label things whenever I do these problems, and I kind of write comments here on what I'm looking at. It really helps me follow my own work. Here I like literally just wrote out what I was doing. Do use your comments, like use comments, use good variable names. They're all really helpful. I just wanted to show that to y'all, so that way, if you were like, does it have to be this long of a variable name? It's like, yeah, if it makes it easier for you to do your work, please do that. At the end of the day, that's what matters. That's it. Y'all did great. Y'all killed on a Monday. It's awesome.
Yeah, good job, everyone.
Thank you for hanging out with us. And can you share the solution to us?
Oh yeah, I'll push it to GitHub right now.
Thank you.
Yeah, try problems 2 and 3 if you can first, and then you can check your work.
Yeah, I'll push it whenever Matt gives me the okay. I will push it up there.
We'll push it up tomorrow.
I'll let the boss man tell me when, and then I'll push it there. So tomorrow it is.
All right.
All right, everyone.
All right, thanks everyone. Bye.